Hello and welcome to another session of Introduction to Astrophysical Fluids. In this lecture, we will continue our discussion on the different type of properties or features of MHD fluids, and specifically we will discuss the inviscid invariance of several fluid variables or fluid quantities in the case of MHD. In general, we will assume that the MHD fluid is compressible, but it has a simplistic closure, for example, either isothermal or polytropic. So for most of the cases, we will use the polytropic closure. So first we start with the very fundamental inviscid invariant, which is the invariance or the conservation of mass. So when we talk about, first of all, inviscid invariance, it simply says that we will try to see that which quantities are conserved in time, if the fluid has negligible viscous effects. So for our case, it will just simply give that nu tends to 0, the viscosity, and the magnetic diffusivity also tends to 0. So under this condition, we will investigate which quantities are conserved. Now once again, when we are talking about conservation, as we discussed in one of the previous lectures, while discussing the inviscid invariances for normal hydrodynamic fluid, we said that for the invariance of the extensive quantities, that density corresponding to the extensive quantity should follow a specific, the evolution of the density, should follow such type of equation, which are known as the conservative forms. So if you really remember, then basically the condition for certain extensive quantity V to be conserved to be an inviscid invariant, if we write V is equal to some Vc d tau, where I can also write like this. So whether this is a vector or just I am taking scalar for simplicity. So then Vc is the density of that quantity V. Then in order that V is an inviscid invariant, we have to have this type of equation plus divergence of some flux, and that flux simply says that it should be exactly equal to either the density Vc times the fluid velocity V, or some other quantity which is not exactly equal to Vc, but some other quantity times V. So, and that we sometimes call the current associated with that quantity. So for example, for mass, we just simply identify rho is the, rho is the density of mass and rho v is the mass current. So this type of things are there. So that this simple form, that is the del T of the that density V rho, Vc should be equal to, so that should be exactly equal to 0. So in that case, you can simply say that del Vc del T will be equal to minus divergence of that current. And just writing current instead of flux, because flux can be misleading. Current. And if I can write, then simply del Vc del T is equal to the divergence of some quantity, then actually we are done. And but it is preferable, of course, as you understand, that the divergence should be multiplied with some quantity, some field quantity, with which it is then easy to use the Gauss's divergence theorem. That means if finally we have to, prove that the volume integral of this thing is 0, and for that, if you really understand the Gauss's divergence theorem, this is nothing but the closed surface integral of this current dot in ds. And if that current is proportional to the velocity, or in MHD we will see that it can also be magnetic field, so that in the surface enclosing that volume, okay, at every point of the surface, that V dot NDS or B dot NDS should vanish. Then you can actually justify that this divergence is, this divergence will lead to a vanishing contribution to the del del T of integration over Vc d tau, and thereby confirming the conservation. Okay, so just following the same ethics, we will finally try to show different type of conservation principles. Okay, so let me first erase all those things. I will come into that, and this part I will do actually very thoroughly, so that you can actually know how to do that. Okay, so the first one is, once again, so we start by discussing the implicit invariance of mass. Okay, and this is evident from the basic continuity equation, which simply says that del rho del t plus divergence of rho times v is equal to 0. So then ddt of integration rho d tau, which is the total mass of course, is equal to integration, then ddt will enter inside the integration that you know from mathematics, and that becomes a del del t inside this integration, and then this del rho del t by continuity equation is nothing but minus divergence of rho v. So integration of divergence of rho v d tau is nothing but equal to closed surface integral rho v dot ds, right? Now rho v dot ds at the surface, if you remember, what I said, that at the surface v dot ds should vanish because this is the extreme surface. If so, ds is this direction. If v dot ds is non-zero, that means that we have some component of the velocity in this direction, and it simply says that this cannot be the surface or the boundary surface enclosing the whole fluid, because it simply says that the fluid can come out or can go in, right? So then this is no longer a boundary surface. So in order that this is a boundary surface, v dot nds or v dot ds simply should be 0. Okay, so we just use that and we will get finally this is equal to 0. So ddt of integration rho d tau is equal to 0 and mass is conserved. Then we have another type of conservation principle, and that's a bit subtle, and that is the momentum conservation, which is trivially true for hydrodynamic fluid. Here there is a trick, because the momentum, first of all, this is a vector conservation, so we will somehow write ddt of integration rho v d tau, and that will be simply equal to, if you do the calculation just by using the Navier-Stokes equation including the Lorentz force, you will see that will give you, okay, a divergence of this quantity, and which by using Gauss's divergence law you can simply write minus closed surface integral rho v tensorial v plus p times unit tensor plus, or identical identity tensor, plus b square by 2 mu 0, again identity tensor, minus b tensorial b by mu 0 dot ds. Now the problem is that at this point you can, from this one you can say that this one dot ds would be 0, this one will also be 0, this one will also be 0, but not this one. Okay, so the b cross b b tensorial b dot ds is not necessarily equal to 0, and that's why okay, so for that, so I am not going into the very detail of this part, so you can see any standard book of magnetohydrodynamics. Here the problem is described. So this basically finally causes the momentum, linear momentum in MHD equations not to be conserved. Okay, so just so I mean that is something we have to understand. Okay, however, for hydrodynamic case this term is no longer present, but it is true that you can have this impression that okay, if this is causing problem, okay, then this can also cause problem, but I mean fortunately this does not cause any problem. Okay, now so momentum transformation, so momentum conservation is not a guarantee in magnetohydrodynamics. Okay, I mean rather in ideal magnetohydrodynamics, because in this whole equation, whole discussion, we are talking about inviscid invariance. So the basic equations or the background equations, okay, of our reference, okay, that will simply be the equations of ideal MHD. So I can then write this is ideal MHD. Okay, now I am going very slowly to the most important conservation of magnetohydrodynamics, that is the conservation of total energy. Now we also discussed the conservation of total energy maybe in the case of compressible fluids, but not really very in detail. Here I will just try to do it at least once thoroughly, step by step, so that you can have the idea not only for total energy but also for other type of quantities, how to prove or how to investigate whether the quantity is an inviscid invariant or not. Okay, so we take a barotropic MHD fluid, which is a bit more general than polytropic. So barotropic simply says that the fluid pressure is simply a function of rho only, fluid density. Okay, so the total energy is given by this an integration E d tau, and E is the density, volume density of energy. Okay, and so for a barotropic MHD fluid, we will try to show that the total energy is conserved, because I mean conserved in the absence of any net viscosity or magnetic resistivity, okay, or magnetic diffusivity. So I mean that is something very intuitive, but we now have to give the proper expression for the total energy. Okay, so one we know, that is the kinetic energy part, and which is quite evident, rho u square by 2, that is the kinetic energy density, that is the magnetic energy density b square by 2 mu 0, minus there is another quantity which comes due to the compressibility of the fluid, and for a so there is already an integration. So inside integration, this is the total energy density function, and which will be then integrated over d tau. But this function itself can be, so this compressible energy or the compressible potential energy function is itself derived from another integration. If we, so for for knowing the functional form of that compressible energy, we have to use the corresponding closure, because we have P is equal to P rho, so we have to know the exact functional dependence of P on rho. Okay, and then if we do from rho 0 is some reference value for the density, to some current rho, current means like the instantaneous rho. Okay, and on the this integration is done on P d 1 by rho. Okay, and the whole thing will then be again integrated on, on the whole space, so will be multiplied by d tau, and this will be integrated. So these will be giving us total energy, and people have already have succeeded to show that this is an inviscid invariance. Okay, now in our lecture we will try to show that. Before showing this conservation or the invariance, we discussed two small points. One is that what will be the compressible potential energy function for a simple isothermal fluid having this very simple closure. P is equal to some constant square rho, and this constant is nothing but the sound speed square. So P is equal to Cs square rho. So for that case, this one is the kinetic energy density, this one is the magnetic energy density. Now we have to do something like that, integration minus integration rho 0 to rho P d of 1 by rho, and this d of 1 by rho is nothing but minus d rho by rho square. So finally that will be coming rho 0 to rho P d rho by rho square. So, and this P is nothing but so this P is nothing but Cs square rho. So finally this will become rho 0 to rho Cs square, where Cs square is nothing but a constant, d rho by rho square times rho. So rho square will cancel one density, and you have Cs square d rho by rho. So finally the functional form will be Cs square log rho by rho 0. Okay, and that's exactly what we will use here. And for a polytropic case where P is equal to some constant rho to the power gamma, then if you follow the same formula, okay, and it's you to do now, okay, so do it yourself, then you will see that minus integration P d 1 by rho is simply equal to P by gamma minus 1. Sorry, this is a small p. Okay, so I think there is a small mistake. So that was just a minute. So P d rho, yeah. So I think that this is just a function of P by rho. So there should be, a rho which will be multiplied throughout, because this is only the functional form for the internal energy, or compressible potential energy. So there should be, I'm just writing in red so that you can recognize that there should be a rho multiplied. So rho is the density times the you have to have some function E. So basically the whole thing should be written as rho times E. Okay, if you want to see that, rho times E, and this E, just a minute, this is rho times E, and this rho is this rho, and this E is this functional form. Now how to understand this? So P has a dimension of the velocity square times the density, because it's like Cs squared times rho, and d of 1 by rho has a dimension of 1 by rho. So P times, so Cs square rho by times 1 by rho finally gives you a velocity, the dimension of velocity square. So it is simply this E part, and because the whole thing has a dimension of density times velocity square. Okay, so by this I have just detected the error in my writing, So finally I think this is not a big problem. So I'm just writing once again, so rho will be there. And finally this one, so for P, I mean for polytropic case where P is equal to K times rho to the power gamma, okay, then this is the correct expression, and actually E will then be P by rho gamma minus 1, and then rho times E will be simply P by gamma minus 1. Okay, let me just write once again one thing, it's be small p. Okay, that's the thing we use throughout. Okay, now so now we have to check for polytropic case that integration rho v square by 2 plus b square by 2 mu 0 plus p by gamma minus 1 d tau is conserved. Okay, so as I just said that this one is often expressed as, and that is not the correct case actually, so this one, that should be rho. Okay, so rho times this thing is often expressed as rho E, where E is the compressible potential energy, okay, per unit mass. Okay, so then we are done. Okay. So once again, so for isothermal case, then we agree for isothermal case E is equal to Ca square logarithmic of rho by rho 0, and in case you just choose, just for simplicity, your rho 0 or the reference density is 1, then your log rho 0 is 0. Okay, and then simply is equal to Ca square log of rho. That's exactly what we do when we talk about an isothermal fluid. And for polytropic case, E is equal to P by rho times gamma minus 1. Okay. So here in this, I mean in this lecture, what I will do, I will like derive the, I mean step by step, the conservation or the implicit invariance of the total energy. So as you know that we have to show that E, which I mean the total energy density is this plus B square by 2 mu 0 plus rho E. Okay, and we have to show that E d tau is conserved in ideal MHD. Then we actually have to show that ddt of integration E d tau is equal to 0. That we have to show. So we start by doing, or we have to show integration del E del t d tau is equal to 0. Okay, so we start by different piece of E. First one is this, the kinetic energy term. So del t of rho u square by 2. So I personally prefer writing like this. So this will be rho 2. Now del t of u square is nothing but 2 times u dot del t of u. Okay, so this is nothing but del t of u square. Okay, and then I have another term which is u square by 2 del t rho. Okay, and if you remember the expressions of this these quantities, for example this one, you will see that it will be, so this 2 and 2 will go away, rho u dot within the bracket, I don't know, maybe it is good that I write like this. Okay, I should write like this, maybe it's easier. I mean, we can write in anyways. If this is correct, there is no problem. So minus rho u dot nabla u. So I am just writing the expression for rho times del u del t. Okay, and that is minus rho u dot nabla u minus minus gradient of p plus j sorry, maybe j cross b. Okay, and we are not considering any dissipation. So here we have just used this equation. In case you have forgotten that, we have used this equation. This equation. Okay. Maybe I have made a mistake again in writing this u and v. So please replace every u by v. And then I have another term which is v square by 2 del rho del t, and del rho del t by continuity equation is nothing but is equal to minus divergence of rho v. Okay, so finally what you have is that is equal to, so this is v, so minus v dot rho v dot nabla v minus v dot gradient of p plus v dot j cross b. Okay, yeah, plus or rather minus u square by 2, sorry, not u square but v square by 2 divergence of rho v. Okay, now you see that this one is nothing but, so this one is minus j dot v cross b. Okay, and this is again equal to you know that for ideal MHD case E is equal to minus v cross b, so we have simply this is j dot e. Okay, now that part is solved, so I can simply write now j dot e for this part. Now what about for the others? These I write as it is, and what about these two? This one and this one, what to do with them? So I mean, what we can do, that we will simply try to understand that what this thing is. So I mean, I can do one simple thing, that is, from this one I can write like this. So minus, so this row can come out, so this will be simply rho v dot nabla v. So v dot nabla v has a very popular expression. This is gradient of v square by 2 minus v cross omega. Okay, and then there will be minus v square by 2 divergence of rho v. Okay, so v dot v cross omega, that is 0, because two elements in a scalar triple product are identical, so this is 0. Okay, so we finally have this is equal to j dot e minus v dot gradient of p minus, so rho v dot gradient of v square by 2, okay, I am just taking everything inside the bracket, plus v square by 2 divergence of rho v. So you clearly see from this is nothing but, I just change the color once again, is nothing but divergence of rho v square by 2, or rather another way of writing is rho v square by 2 times v, right? Okay, clear? So if we now check the whole thing, so we have this component, we have this component, and we have one divergence. Okay, so that's already a good thing. So we have some divergence. Okay, then we go to the other expressions. So first we have to take the magnetic energy, the evolution of the magnetic energy density, which gives this expression, and here we have simply 1 by mu 0 once again, so it should be so there will be a half, and 1/2 should come from there, so that will be cancelling out, and so finally we have b dot del t b, and this del t b is nothing but from ideal MHD equation, this is curl of v cross b. Okay, and if this is true, then we can simply write minus, this is exactly equal to minus 1 by mu 0. Now this is, I'm sorry, this should be a dot. Okay, so we can write in another compact form just by using a divergence of so you can simply write this as e minus e actually. So just a minute, let me just check this out. I can write a minus 1 by mu 0, and then I can write this as b dot nabla, a curl of e simply, and then you can write this is equal to minus 1 by mu 0 e cross b plus e dot curl of b. Okay, so yeah, because this one is equal to this one minus this one, so right, and so you have minus divergence of e cross b by mu 0, which you can simply identify as very popular pointing vector, this one. Okay, so pointing vector, right? And the next term simply becomes e dot j. Okay, so I have a minus e dot j, and simply see here you have a plus E dot J. So already this is good, that these two things will cancel each other and we have one divergence, so nothing to worry. Just this part can raise some concern. Okay, so how to get rid of this term? Either we have to make it cancel by other term, or we have to make so that it can combine with other term to give a resultant divergence. Okay, so for that, finally, if we do calculations, so we have to then do the last part of this whole drama, and that will be given by this del t by p by gamma minus 1, and for that the trick is I have to write gamma times gamma minus 1 and then I have to write p by rho times minus divergence of rho u. Okay, this is a very small and elegant homework which you can do. So I just write, you try. So you have this relation P is equal to K rho to the power gamma, and you know del rho del T. So from that you try to find del P del T. And if you do that very carefully, you will see this, you will have finally this equation, this one. Okay, and if you further just decompose all these things, you will see that this equation will be simply equal to minus divergence of rho e v, and once again it should be v, okay, yeah, rho e v minus p times divergence of v. So now you see that, so this is also a very good homework, please do that homework. Now you see that this has a divergence part, so we don't have any problem, and this has a minus p times divergence of v. So it has a minus p times divergence of v, and this part had minus v dot nabla p. So finally, if they are added, you will simply see that they will give something like this, del. So I can just, so we have now two terms other than the divergences. Okay, and who are they? Minus p divergence of v minus v dot p, right? Am I right? Yes. So the combination would give us divergence of PV. Okay, so we are done. Okay, so this is also a divergence. So finally, del T of rho u square by 2 plus b square by 2 mu 0 plus rho e will be simply equal to minus divergence of rho u square by 2 plus p plus rho e times u plus pointing vector. Okay, So once again, finally it is true that we have to, like certify, or we have to ascertain that this one, when we will do this, then it should be like this, and then this will be simply equal to the whole thing rho u square by 2 plus p plus rho e u, sorry, it's a v every time I am making u v. Have I made some other u? Okay, no, not really here, but here yes, v, yeah, okay, v plus e cross b mu 0 d tau. So for this part we don't have, sorry, not d tau, but it should be this. Now as this total part is multiplied with v, we don't have any problem because v is multiplied with ds gives you 0 in the surface. What about this term? So for that I have to write actually E is equal to minus v cross b. So finally then you have two type of terms. In one you will have terms like v dot ds, which is okay for vanishing. There will be another term b dot ds that will also vanish, because otherwise if the magnetic fields just gets out of the boundary surface, simply b dot ds, that means that this is no longer a boundary surface. So both for velocity lines of force, so fluid lines of force, so what we call streamlines, or just the the velocity, just the fluid velocity itself, and the magnetic lines of force, both should be at best tangential to the surface of the boundary. Okay, otherwise if there is non-tangential component, that means something is coming out or something is going in. Okay, so this is no longer a boundary, so they should be 0, finally making the whole thing to be 0, and that finally confirms the conservation of total energy. Now you see, in the case of magnetohydrodynamic fluid, the total energy is consisting of three parts: kinetic energy, magnetic energy, and the compressible energy, which is a kind of potential energy. Okay, and we have seen that in the absence of eta and nu, that means the magnetic diffusivity and the kinematic viscosity respectively, the total energy of an imaged fluid is conserved. Okay, so I will continue this discussion just concerning the other conservation laws. Okay, thank you.